talk about cabin atmosphere control systems, and let's start with pressurization. Now, the whole purpose, the whole idea of pressurizing an aircraft is to allow operation at high altitudes and create an environment to prevent hypoxia. Hypoxia, of course, is lack of sufficient oxygen reaching the brain, commonly caused by flying at too high an altitude without oxygen or without pressurization, because what pressurization does is allow you to fly at the high altitude without worrying about hypoxia. Now, when you pressurize an aircraft, you get a differential pressure, a cabin differential pressure. You've got a certain amount of pressure outside, the ambient or external air pressure, and you have a higher internal or cabin air pressure, and that gives you a pressure differential. So cabin differential pressure is the difference between the ambient or external air and the internal air pressure. The cabin differential pressure can be measured on the cabin differential pressure gauge. It's got nothing whatsoever to do with mean sea level, and it does not measure the cabin pressure controller setting. Now, when you pressurize an aircraft, you impose stress on that aircraft, and the kind of stress you impose is called tension stress. When that aircraft is pressurized, what you have is higher pressure air inside the aircraft than there is outside in the ambient atmosphere, and it's pressing outward on the fuselage, and that kind of stress is called tension stress. And you can measure how much stress you're putting on the aircraft by how much the cabin differential pressure is. Now, the fuselage is designed to only take a maximum amount of differential pressure because it can only take a certain amount of stress. And one way to get rid of excess pressure, if it looks like you're about to get it, is to open the dump valve. The purpose of the dump valve in a pressurization system is to relieve all positive pressure from the cabin. So when you open the dump valve, basically you've taken the cabin to normal atmospheric pressure, whatever that may be, and you've gotten rid of the differential, the pressure differential, and you have relieved the positive pressure from the cabin, and that gets rid of the stress on the aircraft. Now, a pressurized aircraft is designed to take tension stress, which means stress from the inside of the aircraft pushing out with higher pressure air inside the aircraft than surrounds it. It is not designed to take negative pressure, and so aircraft have a negative pressure relief valve in the pressurization system, and what that does is it prevents the cabin altitude from becoming higher than the actual altitude of the airplane. Another way to put that is it prevents the pressure inside the aircraft cabin from being lower than the ambient atmospheric pressure around it. It prevents having pressure press inward on the aircraft as opposed to having it press outward the way that a pressurized aircraft is designed to do it. So it prevents the cabin altitude from becoming higher than the airplane altitude, and the way it does that is simply lets ambient outside air in if the cabin altitude is getting higher than the actual airplane altitude is. Now, in general, it's not a good idea to have a cabin pressurized when you're on the ground. So to avoid that happening, the main landing gears on many aircraft will have a micro switch on them, and that micro switch prevents the cabin from being pressurized on the ground. So the pressurization is prevented by the pressurization main landing gear operating switch. Basically what happens is that when the oleo compresses, indicating that there's weight on the wheels, therefore that you're on the ground, that switch will make sure that the cabin is not pressurized, and that allows you to open the cabin door more easily, and also make sure that when you do open the door you don't get blown out of it because the cabin is pressurized. It's not done by regulators or relief valves in the cabin, but by that pressurization ignition main landing gear operating switch. Now, what exactly constitutes a pressurization cycle in an aircraft? Well, a pressurization cycle is considered to be one complete series of events or operations that occur regularly in the pressurization system. It is not one takeoff and landing, because it could be a very short, low-altitude flight where you don't pressurize at all. And it is not reaching maximum pressure differential in the aircraft, because if it's a low-altitude flight, you might not get all the way to max pressure differential. It's one complete series of events or operations that recur regularly in the pressurization system that constitutes that pressurization cycle. Now, cabin pressurization is based on, one way or another, stuffing a lot of air into the aircraft cabin and then controlling the outflow of that air out of the back of the cabin. One way to stuff a lot of air into the cabin, particularly used in large piston engine aircraft that are going to be pressurized, and also in some of the earlier jets that didn't have all that much engine power, is an independent cabin air compressor. Now, an independent cabin air compressor may use bleed air from a turbine engine in order to operate the compressor, or it can be gear driven through an accessory drive gearing off of the engine. But in either case, what that cabin air compressor is doing is, whether it's powered by bleed air off the engine or whether it's powered by an accessory gear drive, that compressor is independently pulling air in from outside and taking that air and compressing it and putting it into the aircraft cabin. It is not taking bleed air directly from the engine and putting it into the cabin. If the compressor is driven by the engine, it's still pulling in outside air and using that, compressing that, and putting it into the aircraft cabin. Now, sometimes these independent cabin air compressors can become disengaged or quit functioning for one reason or another. And if that happens, you do not want to lose the pressurization air. And that is prevented from happening by a check valve in the delivery air duct. So when they ask you if the cabin air compressor becomes disengaged, what prevents a loss of pressurization, it's not valves in the back of the airplane they're talking about. What it is a check valve in the delivery air duct that keeps the air from coming back out through the compressor if that cabin air compressor becomes disengaged. Okay, the independent cabin air compressor like that is typically what you would find on a large piston engine aircraft to pressurize the aircraft. But if you're working with a jet aircraft, what you're typically going to be using is bleed air instead. They take air, hot compressed air, off the compressor section of the turbine engine, and that provides bleed air for the pressurization and air conditioning systems of a jet aircraft, because modern jet engines have more than enough air, not only for the engine operation, but also for the cabin air system, for the cabin pressurization. And you can use that bleed air from the turbine engine compressor because generally it is free from contamination and can safely be used for cabin atmospheric air. Now, in a pressurization and air conditioning system, you very commonly will have a jet pump in the system. And the purpose of the jet pump, when you've got it, is the same idea that a jet pump provides in a fuel system, only it's working with airflow instead of fuel flow. What it does is augment the airflow in some areas of the aircraft. And the way they do that is they take high pressure, high volume bleed air, and they run it through this jet pump. They run the high pressure air through the jet pump and use that to pull in other air, a high volume of air under lower pressure. So the jet pump is used to augment the airflow, get more airflow in some areas of the aircraft. Now, you want to be able to control the cabin pressurization, so here's the pressurization control panel in a 727. A pressurization controller has three things that it really has to have in order to be able to control the cabin pressure the way that the pilot wants it. And that is barometric pressure, cabin altitude, and cabin rate of change. Barometric pressure is the ambient outside pressure. Cabin altitude is the pressure inside the cabin, and then cabin rate of change is how fast the cabin is going up or down, and those three inputs allow the pressurization controller to do what the pilot wants. Now, as part of that pressurization control system, there is a cabin pressure regulator, and the cabin pressure regulator is controlled by cabin air pressure. In other words, you basically say, I want the cabin to be this altitude, and then by knowing what altitude the cabin air pressure actually is, the regulator will open or close the outflow valve in the back to keep the cabin pressure where you want it. We're going to talk about that outflow valve a lot more in just a minute. The cabin pressurization system, or ranges, have basically three modes or ranges of operation. What you've got in that cabin pressurization system is an unpressurized mode, a differential mode, and an isobaric mode. Unpressurized, differential, and isobaric. Unpressurized is pretty obvious. Unpressurized basically is you don't have the pressurization system working at all. Whatever air you've got in the cabin is the same as ambient, normal outside air, and that's what small general aviation aircraft have got. No pressurization at all. The isobaric range. The isobaric range means that you are controlling the cabin altitude, you are controlling the actual pressure in the cabin. You have it set for 5,000 feet of altitude or 8,000 feet of altitude or whatever actual cabin altitude you want. The differential range on the pressurization controller means that you can no longer control the actual altitude of the cabin because the aircraft is high enough that that would give too much pressure differential. So in the differential mode, what the pressurization system is controlling is the differential between the pressure inside the aircraft and the pressure outside the aircraft and maintaining the maximum differential that is allowed. And whatever the cabin altitude works out to be, that's what it'll work out to be by keeping the differential pressure within the range that the aircraft is allowed to carry to keep from overstressing the aircraft. Now, we've been talking about the outflow valve. Basically, what the outflow valve does, and located in the back of the pressurized aircraft, is controls the pressurization, the cabin pressure on an aircraft. And the way it does that is it gets rid of all the cabin pressure in excess of the amount for which it's set. So what you're doing is stuffing air in the front of the cabin, either by bleed air off the engines or through an independent cabin air compressor, and then this outflow valve in the back of the cabin will dump any air over the amount that you have called for in the pressurization controller. So what really controls the pressurization of an aircraft cabin is the outflow valve, not the input coming in, but how much air you allow to go out the back of the aircraft through that automatic outflow valve. So the primary function of the outflow valve is to maintain the desired cabin pressure. That's the primary function of the outflow valve. And as you can see by that, the cabin pressure control setting is going to have a very direct influence on the outflow valve opening. If you ask for a higher cabin altitude, then that outflow valve is going to be open more to let more air out so that you don't have as much air pressure in the cabin and you have a higher cabin altitude. Now let's assume that you're climbing to altitude, but the cabin rate of climb is too great. You're looking at the cabin rate of climb indicator in the pressurization system, and the cabin is climbing too fast. The cabin rate of climb is too great. What, the FAA says, do you want to do about that? The pressurization control should be adjusted in that case to cause the outflow valve to close faster. If the cabin is climbing too fast, it means that too much air is going out the outflow valve in the back, not enough is staying in the cabin, and that means that outflow valve needs to close faster, needs to get more closed quicker, and that will retain the air in the cabin and slow down the rate of climb of the cabin. So close the outflow valve faster if the cabin is climbing too fast. Pressurization is wonderful. But what if you don't have pressurization, or you just simply need a backup system. In that case, we use an oxygen system. This guy has not only got his oxygen mask on, he's also got smoke goggles on, but the oxygen is what you would have to use if you either did not have a pressurized aircraft and you're flying at altitude, or for some reason the pressurization system failed. Now, the oxygen that is used in aircraft systems is not the same as medical or hospital quality oxygen. The oxygen used in aircraft systems is 99.5% pure. It is water-free for all practical purposes. And the reason we say it's not hospital quality is because hospital or medical quality oxygen usually contains water, and you do not want water in aircraft oxygen systems. The primary difference then between aviation breathing oxygen and most other types of commercially available oxygen is the amount of water, the amount of moisture in it, because the aviation breathing oxygen has had the water and the water vapor removed. Now, if you're going to install a high pressure oxygen cylinder in an airplane, that high-pressure oxygen cylinder has to meet certain specifications. And those specifications it has to meet are the ones of either the Interstate Commerce Commission or the Department of Transportation. Both the Interstate Commerce Commission and the Department of Transportation have specifications for high-pressure oxygen cylinders, and the cylinder has to meet one of those two sets of specifications. High-pressure cylinders, by the way, that do contain oxygen for aviation use can be identified pretty easily because, first of all, they're green, and secondly, they're going to have the words aviators breathing oxygen stenciled on them in 1-inch white letters. So they're very recognizable and very identifiable. Now, when you're working with a built-in oxygen system in an aircraft, in some of those systems, you will have a pressure reducer valve. And the whole purpose of the pressure reducer valve in the system is to change the high cylinder pressure, because in the cylinder you've got pretty high oxygen pressures, 1800 psi and so on, down to low pressure for the oxygen system as it goes through the aircraft. If that pressure reducer fails, what will happen is a pressure relief valve will prevent high-pressure oxygen from entering the system downstream. Basically, what it will do is it will blow out the oxygen out plugs in the fuselage skin, because that way the high-pressure oxygen will get vented overboard rather than going through the system and creating problems in a system that is designed to take low-pressure oxygen as opposed to high-pressure oxygen. And this is what that plug looks like that you'll find on the fuselage skin. If that green thermal expansion disc is missing, that means that you may have had an overpressure event in the aircraft oxygen system. Remember, disc is on the outside of the fuselage. It is not in the cockpit or on the oxygen regulator. Now, if you're flying in a normally unpressurized aircraft, normal, small general aviation aircraft, something like that, the oxygen systems are generally of the continuous flow or pressure demand types. The continuous flow oxygen system uses the rebreather Bragg principle. So in this continuous flow oxygen mask, you've got oxygen coming in through a tube, but as the person breathes in and out, that breath is collected in this rebreather bag here, so that as you breathe each time, you're not getting pure oxygen, you're getting oxygen that is mixed in with normal air, and that gives you less of a concentrated mixture. The continuous flow oxygen system uses a rebreather Bragg principle. Now, how do you control the amount of oxygen that's going to be delivered to a mask like this? A calibrated orifice in the system. In other words, where that mask plugs into the aircraft oxygen system, there will be a calibrated orifice, a hole of a certain size, and that controls the volume of oxygen, the amount of oxygen that will be delivered to that mask. Now, the type of mask that the crew would typically use, and particularly in an aircraft that is normally pressurized, is a diluter demand oxygen regulator system. In the diluter demand oxygen regulator system, whenever the user breathes, the demand valve operates. In the other system, the continuous flow, the oxygen does just what its name says. It flows all the time. In the diluter demand system, you only get oxygen when the user breathes, and that is much more conservative in the use of oxygen because you don't have it flowing out into the atmosphere when the person isn't breathing and isn't using it. Now, you will have very typically an airflow metering aneroid in the demand regulators on this type of oxygen mask. And the purpose of that airflow metering aneroid is to regulate the airflow in relation to the cabin altitude when the mask is set in the diluter demand position. Bunch of words there. What exactly does it mean? A mask like this can be set for either normal, what they call the diluter demand position, or it can be set for 100% oxygen. Most of the time, at most altitudes, you do not need 100% oxygen in order to have adequate oxygen because there is a certain amount of oxygen in the air. So what it's got is an aneroid in the demand valve here, and what that does is it senses the outside pressure, and then it allows a certain amount of ambient outside air to come in when you breathe on the oxygen so that you get some oxygen and some outside air, and the amount of outside air is reduced and the amount of oxygen from the mask is increased as you go to a higher and higher altitude. So that aneroid regulates the airflow, the ambient airflow, in relation to cabin altitude when it's in the diluter demand position. Now, sometimes it's useful to have an oxygen system for emergency or backup use. And sometimes that emergency or backup oxygen will be a chemical oxygen candle system. A chemical oxygen candle system is the least complicated and requires the least maintenance as far as an emergency or backup use is concerned. The basic problem with it is once you start that kind of oxygen going as a backup, you're going to go all the way through that chemical oxygen candle. There isn't any way to shut it off or stop it once you start it. So you're going to use it all up in that particular time. But it's not complicated and requires very little maintenance. So the characteristics that you have of a chemical or solid-state oxygen system are that you've got a lot of storage capacity. You have a volume storage capacity of about 3 times that of compressed oxygen. That's one of the advantages of that solid-state oxygen system as a backup. And also, the system generators are inert below 400 degrees Fahrenheit, even under severe impact. What that means is that you're not going to have an explosion, you're not going to have a fire problem with it as long as the temperature is below 400 degrees Fahrenheit, even if you have a crash, if you have a severe impact. So it's a safe way to go, and it's got a lot of oxygen volume. Another alternative for an oxygen system has been used in military aircraft, although not in civilian aircraft yet, and that is mechanically separated oxygen system. A mechanically separated oxygen system uses a molecular sieve, and what that molecular sieve does is basically filter out the oxygen and put it into the system and reject the other gases in the air, and that creates basically or separates oxygen from the air, a mechanically separated oxygen system. Now, there's some very important things to know about oxygen system maintenance, some precautions that you have to observe if you're working on an oxygen system. First of all, any tools and any equipment that you're using to service oxygen must be kept free from oil and grease. Oxygen is very flammable, and you can get spontaneous combustion if you have anything that has oil or grease on it around the oxygen system when you're working on it. You want to make sure that you display no smoking placards when you're working on the oxygen system because, again, oxygen is extremely flammable. Because of that, you want to make sure to provide adequate firefighting equipment in the area when you're working on an oxygen system. And you do not want any sparks, so you want to avoid checking aircraft radio or electrical systems. You don't want any sparking problems. Now, you may need to check the serviceability, determine the serviceability of oxygen cylinders. They have to be the correct type, and they have to have been hydrostatically pressure tested with water within the proper time interval. And what hydrostatically tested means is that they put water pressure inside it and pump it up to see if the thing cracks or breaks, and when they take it up to the pressure limits that they're supposed to for proper testing. A high-pressure oxygen cylinder has to be hydrostatically tested every 5 years. A standard weight high-pressure cylinder needs to be tested every 5 years. Now, how do you know if an aircraft oxygen bottle can be considered airworthy? Well, it has to have been hydrostatically tested, and it needs to have 3 things stamped on the cylinder near the neck of the bottle. And those 3 things are the test date when it was hydrostatically tested, the DOT number, and the serial number of the bottle. What does not have to be stamped up there is the manufacturer's name. The manufacturer's name is not one of the required 3 items. Now, in addition to standard bottles, there are also lightweight cylinders, known as a DOT 3HT oxygen cylinder. They get less time between hydrostatic testing. They have to be hydrostatically tested every 3 years instead of every 5. And on the lightweight cylinders, they have to be retired from service after 24 years or after 4,380 filling cycles, whichever one occurs first. So they get a long life, 24 years, but they don't get an awful lot of filling cycles, only 4,380. On the other hand, a third type of oxygen bottle, a composite oxygen bottle that conforms to DOT E8162, has a service life of only 15 years, but on the other hand, it gets 10,000 filling cycles, whichever one comes first. Now, the FAA will try and mix you up between the requirements as far as the lightweight cylinders, the 3HT cylinder, and the composite oxygen bottles are concerned. The lightweight cylinders have a longer life, 24 years, compared to 15 years for the composite, but on the other hand, the composite bottles have more than double the filling cycles, 10,000 filling cycles for the composite bottles. So think of the composite bottles as having lots of nice round numbers, 15 years of service life, and 10,000 filling cycles, whichever one comes first. Composite oxygen bottles, by the way, are aluminum bottles that are wrapped with Kevlar.